Hello and welcome back. In today's video, I'm overclocking the AMD Ryzen 9 9950X3D processor all the way up to 5900 MHz using the Asus ROG Crosshair X870E Hero motherboard and AIO cooling. I do this by using the advanced overclocking tools of the Precision Boost Overdrive 2 toolkit, namely Curve Shaper. In this video, I break down the Ryzen 9 9950X3D tuning process into 5 unique overclocking strategies for beginner and advanced overclockers. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that I'm using in this guide. The AMD Ryzen 9 9950X3D is part of AMD's Zen 5 based Ryzen 9000 desktop processor product line, codenamed Granite Ridge. The Granite Ridge processors were introduced on June 2nd, 2024 during Computex. The Ryzen 9 9950X3D succeeds the 16-core Zen 4 Ryzen 9 7950X3D, which we overclocked in SkatterBencher number 56. It has a base clock of 4.3 GHz and a listed boost frequency of up to 5.7 GHz. Unlike its predecessor, the TDP is now 170 watts. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course we have to check the performance at default settings. The default Precision Boost 2 parameters for the Ryzen 9 9950X3D are as follows. Here's the benchmark performance at stock. Here are the 3D Mark CPU profile and OCCT benchmark scores at stock. Here are the AIDA64 memory benchmark scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 4292 MHz and CCD1 effective clock is 4326 MHz with 1 volt. The average CPU temperature is 68.9 degrees Celsius. The average CPU package power is 184.3 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 4681 MHz and CCD1 effective clock is 4783 MHz with 1.085 volts. The average CPU temperature is 71.7 degrees Celsius and the average CPU package power is 197.4 watts. Of course, we can increase the power limits by using Precision Boost Overdrive, and that's exactly what we'll do in our very first overclocking strategy. But before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply take advantage of enabling AMD Precision Boost Overdrive and enabling AMD EXPO. With the launch of Zen 5, AMD introduced an improved version of their Precision Boost Overdrive 2 Overclockers toolkit, which allows us to fine-tune some of the parameters governing the Precision Boost 2 technology. The Precision Boost Overdrive 2 toolkit for Zen 5 Ryzen processors includes the overclocking knobs from Zen Plus, PPT, TDC and EDC, Zen 2, Boost Override and Scalar, Zen 3, Curve Optimizer, and the newly announced Curve Shaper for Zen 5. There are essentially 3 levels of Precision Boost Overdrive. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and to a lesser extent the TDC and EDC will help unleash the frequency in multi-threaded workloads previously limited by the PPT. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD technology that enables ubiquitous memory overclocking for AMD platforms supporting DDR5 memory. EXPO allows memory vendors, such as G.Skill, to program higher performance settings onto the memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting. Note that I had to enable EXPO 1 to ensure my memory kit passed the OCCT memory stress test, as EXPO 2 didn't pass the test. Upon entering the BIOS, The boost frequency at one active thread is about 5522 MHz, and the average boost frequency gradually trails off to 5074 MHz when all cores are active. In light single-threaded workloads, all cores in CCD0 can boost to over 5.55 GHz, and all cores in CCD1 boost to over 5.7 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. While the 9950 X3D is limited by power, as we'll see in the OCCT stress test results, in normal workloads it doesn't seem to be too limited. We see a little bit of an improvement in multi-threaded applications, and thanks to the extra memory performance, a little more improvement in workloads that are also memory dependent. The geomean performance improvement is plus 1.99%, and we get a maximum improvement of plus 22.43% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 4692 MHz, and CCD1 effective clock is 4786 MHz with 1.101 volts. The average CPU temperature is 87.9 degrees Celsius. The average CPU package power is 270.4 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 4988 MHz, and CCD1 effective clock is 5108 MHz with 1.208 volts. The average CPU temperature is 93.6 degrees Celsius. The average CPU package power is 294.4 watts. In our second overclocking strategy, we tuned the CPU's Precision Boost boosting algorithm using some of the tools that are available in the Precision Boost Overdrive 2 toolkit. Fused maximum frequency, or Fmax, is one of the Precision Boost infrastructure limiters constraining the CPU performance. Basically, it defines what is the maximum allowed operating frequency of your processor. On dual CCD processors like the Ryzen 9 9950 X3D, each CCD will have its own Fmax. The Fmax for CCD0, the one with the 3D V-cache, is 5550 MHz, and the Fmax for CCD1 is 5750 MHz. Boost Clock Override, or Fmax Override, is one of the tools available in the PBO Overclockers toolkit. It allows the user to override the arbitrary clock frequency limit between minus 1000 MHz and plus 200 MHz in steps of 25 MHz. So with a plus 200 Fmax boost override, the new maximum boost frequency for the CCDs is 5750 MHz and 5950 MHz. It's important to note that the Fmax boost override only increases the ceiling and doesn't act as an offset. At the end of the day, the Precision Boost algorithm still determines what's the actual maximum frequency that the processor will be running at. Scalar is a tool that allows us to override the warranted silicon stress level, or FIT. You can adjust the maximum allowed fit level to 10 times higher than the factory fused limit. While the tool offers precise granularity, typically you'll find the available options to range between 1x and 10x in steps of 1 multiple. The effect of increasing scalar is that the Precision Boost algorithm will pursue higher voltages because it's less concerned with CPU lifespan. The relevance of this tool can vary architecture to architecture because it's just one of the limiters that is constraining the operating voltage. For the Zen 5 Granite-rich processors, it appears Scalar is making a comeback in the overclocking strategies because the chips are voltage limited. When all cores are active, the maximum voltage is 1.35 volt. With a 10x Scalar, we find that in all-core workload, the maximum voltage increased from 1.35 volt to 1.36 volt. That's not a big increase, but in voltage-constrained scenarios, every little bit helps. Curve Optimizer is arguably the most important tool for overclocking or tuning AMD Ryzen CPUs. It's most commonly known for its undervolting capabilities. However, for AMD CPUs, it kinda also works as an overclocking tool. To explain why that is, let's start with the basics, the voltage frequency curve. Simply put, a voltage frequency curve describes the relationship between an operating frequency and the voltage required to operate at that frequency. Every modern SoC has a factory-fused voltage frequency curve and uses this to dynamically adjust the power consumption depending on the workload needs. Here's the default voltage frequency curve of my Ryzen 9 9950X3D processor. You'll notice that there are in fact two curves, and that's because the Ryzen 9 9950X3D has two CCDs with quite different characteristics. We can immediately make a simple and redundant observation. The higher the frequency, the higher the voltage. For example, CCD0 requires only 1.1 volt for 4850 MHz. However, we need over 1.25 volt for 5350 MHz. This also applies to CCD1. 1.1 volt gets us 4925 MHz, whereas we need 1.25 volt for 5550 MHz. Although it's not obvious from the VF curve, the maximum allowed voltage is 1.35 volt when all cores are active. The Precision Boost 2 algorithm utilizes the VF curve to find what's the maximum possible frequency at 1.35 volt. With the default curve, that's 5500 MHz for CCD0 and 5675 MHz for CCD1. As I showed just a couple of minutes ago, we can use the Fmax boost override tool to increase the Fmax by another 200 MHz. That further extends the default VF curves. Note that all other precision boost rules still apply. So even though we have a higher frequency ceiling, because the frequency points are above the 1.35 volt threshold, we won't see those frequency boosts in all core workloads, however light they may be. If we set a negative curve optimizer, we can shift the entire voltage frequency curve along the voltage axis, and suddenly we need a lot less of voltage for every operating frequency. For example, for 5.4 GHz, CCD0 needed about 1.273 volt, and CCD1 needed 1.199 volt by default. But with a minus 20 curve optimizer, now we only need 1.157 volt and 1.124 volt respectively. Moreover, the frequency is also boosting higher. The highest frequency with all 16 cores active has increased by 100 MHz from 5500 to 5600 MHz on CCD0 and from 5675 to 5775 MHz on CCD1. These frequencies are now possible because our curve optimizer undervolting pulled them below the 1.35 volt threshold. Curve Optimizer is a powerful tool. It's simple, but not simplistic. And the more you dig into the details, the more you become aware of its intricacies and how it applies to your daily overclock. We use Curve Optimizer most commonly by applying a negative value to undervolt. And that helps in two ways. First, undervolting lowers the operating voltage, temperature, and power consumption. Second, as a consequence, the Precision Boost 2 algorithm can leverage the additional headroom to boost to higher frequencies. So you tend to get lower temperatures and higher performance. It's a win-win. However, there are a couple of caveats to tuning with Curve Optimizer. One, Curve Optimizer impacts the entire voltage frequency curve, so it affects stability across the entire range of operating frequencies, from 600 to 6000 MHz. And two, the same Curve Optimizer value impacts differently across the curve. Curve Optimizer is available on a per CPU, per CCD, and per core basis. The manual tuning process for Curve Optimizer can become quite convoluted because the tuning process spans a wide range of workloads, going from heavy all-core workloads all the way to light single-threaded workloads. I want to emphasize this point and refer to my Ryzen 9 9950X overclocking guide, where I demonstrated that the VF curve changes depending on the workload. With a dynamic voltage frequency scaling technology like Precision Boost 2, it's vital to test a wide variety of scenarios as opposed to just heavy all-core workloads pushing the power consumption to its limit. Sometimes your all-core AVX workload can be entirely stable, but you get blue screens in games. I identified 4 typical workloads that tend to show early signs of instability. So when I increase the negative curve optimizer setting in steps of 5 points, I quickly check stability with each of these applications. Once I find an instability, I back off on the curve optimizer and check stability across the benchmark suite. For dual CCD Ryzen CPUs, I strongly recommend to set a per CCD curve optimizer because the CCDs are usually quite different in quality. They have a different Fmax after all. With this CPU, I could set CCD0 to -25 and CCD1 to -20. Be aware, however, that curve optimizer impacts the entire curve, also the part that we extend with Fmax Boost Override. And sometimes that can result in instabilities because those really high frequencies also need high voltage. I found that for my CPU with the -25 and -20 curve optimizer settings, I couldn't increase the Fmax Boost Override beyond +50 MHz. Practically, that means the CPU would boost more aggressively in all core workloads, but would be limited to 5600 and 5800 MHz for CCD0 and CCD1 respectively. Upon entering the BIOS, the boost frequency at one active thread is about 5675 MHz, and the average boost frequency gradually trails off to 5138 MHz when all cores are active. In light, single-threaded workloads, all cores in CCD0 can boost to over 5.6 GHz, and all cores in CCD1 boost to about 5775 MHz. We reran the benchmarks and checked the performance increase compared to the default operation. Fmax Boost Override, Scalar, and Curve Optimizer work together to provide us with higher and longer frequency boosts in all kinds of workloads. We find that the performance improves across the board in pretty much every workload except gaming, where the improvement is not so visible. Geomean performance improves another 2 percentage points, and we get a maximum improvement of plus 23.45% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 4988 MHz and CCD1 effective clock is 5086 MHz with 1.083 volts. The average CPU temperature is 89.1 degrees Celsius. The average CPU package power is 267.3 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 5129 MHz and CCD1 effective clock is 5177 MHz with 1.114 volts. The average CPU temperature is 78.7 degrees Celsius. The average CPU package power is 236.9 watts. In our third overclocking strategy, we try to tune the memory subsystem. Now, on AMD Granite Ridge Ryzen 9000 CPUs, the memory subsystem consists of three major parts: the Infinity Fabric, the memory controller, and the system memory. We also refer to these as the F clock, the U clock, and the M clock. First generation Ryzen overclockers know that these parts used to be tightly coupled together, but on modern Ryzen processors like the Ryzen 9 9950X3D, we can tune them independently. The fabric frequency, or F-clock, is generated by the SLC PLL derived from a 100 MHz reference clock input. The reference clock is multiplied by the F-clock ratio, which you can configure in the BIOS. The standard operating frequency of the Infinity Fabric is 1800 MHz, but on many motherboards you'll find it runs over 2 GHz when Precision Boost Overdrive is enabled. That said, it doesn't seem there's much overclocking headroom beyond 2 GHz. I managed to set 2200 MHz for this overclocking strategy, however, anything higher couldn't boot reliably, not even with voltage adjustments. Speaking of which, the Infinity Fabric voltage is provided by the VDDG voltage supply, derived via an integrated voltage regulator from the VDDCR miscellaneous voltage rail. AMD Granite Ridge has two DDR5 Unified Memory Controllers, or UMC in short, and each provides two 32-bit memory channels. The memory controllers are located on the I/O die and are identical to the memory controllers of the Ryzen 7000 Rafael processors. The Unified Memory Controller Frequency, or UClock, is derived from the UMC clock, one of the SLC PLLs. The memory controller frequency is tied directly to the system memory frequency. It can run either at the same or half its frequency. At default, the memory controller runs at the same frequency as the system memory at 2400 MHz. However, we find that when enabling EXPO, the motherboard auto rules will automatically drop the memory controller frequency to half the memory frequency. We could easily force the memory controller to run at the same frequency as the system memory frequency by setting uclock div1 mode to uclock equals memclock. However, that's only possible if we run the memory at around DDR5 6000. Since our memory is running at DDR5 8000, we're forced to maintain a uclock frequency that's half that of the memory frequency. The VDDCR SoC voltage rail provides the external power for multiple internal voltage regulators on the SoC for various IP blocks, including the memory controller. The VDDIO MEM voltage rail is related as it provides the external power for the VDDP DDR5 bus signaling. The last piece of the memory subsystem performance is of course the system memory. And to tune the memory timings, I rely in part on the ASUS Memory Presets technology. ASUS Memory Presets is an ASUS overclocking technology that provides a selection of memory tuning presets for specific memory ICs. The presets will adjust the memory timings and voltages. The ROG Crosshair X870E Hero motherboard sports 14 memory profiles for a variety of memory ICs and configurations. Since we're interested in simply adjusting the memory timings, we can try the Hynix 7600 MHz 1.45 volt 2x16GB single rank preset. It's the first time that I'm trying to run DDR5 8000 with an AMD Ryzen CPU. Unfortunately, the EXPO profile worked out of the box. But to tune the subtimings, I had to start from scratch. The Hynix 7600 memory preset turned out not to be stable, as it would throw errors in the OCCT memory stress test almost instantly.
An error has been detected.
To fine-tune the timings, I tried setting certain timings back to its EXPO value until I found the timings that caused the errors. To speed up the process, I grouped together the following timings. By checking the impact of adjusting each group's memory timings, I found that it were the L and S suffix subtimings causing the memory instability. By relaxing those just a bit, the memory was stable. Here are the final optimized memory timings for this memory kit. After the tuning, our ADA64 performance improved quite significantly. We got about plus 50% extra bandwidth and plus 25% better latency by enabling EXPO. The memory tuning then added another 12 to 15% on top of that. Upon entering the BIOS, We reran the benchmarks and checked the performance increase compared to the default operation. As we've seen with other modern platforms, tuning the memory timings can have a not insignificant impact on system performance, especially in workloads which are memory dependent. We see this behavior in specific multi-threaded workloads like Y-Cruncher, AI Benchmark, and Geekbench. Also, we can see some stellar impact in certain games. The geomean performance improves another 1.85 percentage points, and we get a maximum improvement of plus 47.85% in PY prime. In the fourth overclocking strategy, we turn to Curve Shaper to address some of the limitations that we encountered in OC strategy number 2. Specifically, I want to use Curve Shaper to stabilize Fmax Boost Override at plus 200. And if possible, I also want to figure out if there's some additional undervolting headroom for all core workloads. Curve Shaper is the latest tool of the Precision Boost Overdrive 2 Overclockers toolkit, and it was introduced alongside the Ryzen 9000 CPUs. I already covered this tool at great length in different videos on this channel. In theory, it seems Curve Shaper is pretty straightforward. You get 15 additional tunable points across the VF curve. But the devil is in the details because AMD's Precision Boost 2 technology doesn't really work with VF points. So instead of getting a list of specific tunable VF points, we get 5 frequency regions and 3 temperatures. The regions have a bit of a vague terminology and are not clearly defined. The temperature points are more straightforward as they're defined as -5, 50, and 90 degrees Celsius. The idea of Curve Shaper is that you can tune specific parts of your VF curve. For example, you could say that you only want to undervolt in the high frequency range at high temperatures. For example, if you want to tune for an all-core workload. In our case, we want to use Curve Shaper for 2 reasons. First, we want to constrain the undervolt in the peak frequency region to stabilize the Fmax plus 200 setting. And 2, we want to explore additional undervolting opportunities for all core workloads. For the first objective, we can use Curve Shaper values for high and maximum frequency regions. For the second objective, we can use negative Curve Shaper values for low and medium frequency region. Let's get a bit more practical with the process. Similar to Curve Optimizer, the tuning process for Curve Shaper can become quite convoluted because not only do we have to think about the entire VF curve, which ranges from frequencies for all core workloads all the way to single-threaded workloads, we also have to keep in mind that we have these different regions and different temperature points. The first goal was to ensure stability at the highest peak frequencies. So I set the Fmax Boost Override to plus 200 and look to adjust the high frequency and max frequency Curve Shaper parameters. Appropriate stability tests for this purpose are single-threaded and all-core light workloads, such as Cinebench R23-1T and Y-Cruncher BKT. I found it very tricky to get stability with max frequency Curve Shaper below -10, while the high frequency Curve Shaper point could go to -25. That lines up with the instability issues we saw in OC strategy number 2 with a more aggressive curve optimizer and a big Fmax boost override. The second goal was to explore any additional undervolting opportunities in heavier all-core workloads. For this purpose, we can use the low and medium frequency Curve Shaper points. I found that I could max out the undervolt at -30 Curve Shaper. The min-frequency Curve Shaper point isn't that useful, as we typically don't go that low in boost frequency in any kind of workload. Since it would affect the voltage at idle, it's recommended to keep it at default. That can also help alleviate rare instabilities where the frequency is boosting from idle to max frequency in ultra-light loads. Here's the resulting curve with a low and medium Curve Shaper of -30, a high frequency Curve Shaper of -25, and a max frequency Curve Shaper of -10. We can compare it with the curve optimized curve from OC strategy number 2. We can clearly see the trade-off between the extended frequency range and the use of less aggressive undervolting at the upper end of the curve. However, we squeeze a little more frequency at the lower end of the curve because of the more aggressive undervolt with Curve Shaper. Curve Shaper is a very powerful tool, and this OC strategy clearly highlights its core strength. It allows us to change the undervolt in different areas to maximize our high frequencies and maximize our medium frequencies. Upon entering the BIOS, the boost frequency at one active thread is about 5,588 MHz, and the average boost frequency gradually trails off to 5,160 MHz when all cores are active. In light, single-threaded workloads, all cores in CCD0 can boost to over 5,630 MHz, and all cores in CCD1 boost to over 5.8 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. While we're now seeing a maximum frequency boost higher than when using Curve Optimizer, the impact in actual workloads is rather limited. So we get ever so slightly better performance across the board, but nothing to write home about. The geomean performance improves another 0.5 percentage points, and we get a maximum improvement of plus 47% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 5021 MHz, and CCD1 effective clock is 5088 MHz with 1.082 volts. The average CPU temperature is 89.44 degrees Celsius. The average CPU package power is 272.2 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 5155 MHz, and CCD1 effective clock is 5209 MHz with 1.126 volts. The average CPU temperature is 77.4 degrees Celsius. The average CPU package power is 240.7 watts. In our final overclocking strategy, we're pursuing a manual overclock. Now, you could argue that manually overclocking an AMD Ryzen CPU doesn't really make a lot of sense, because when you switch to OC mode, so you manually set the frequency and the voltage, you disable all Precision Boost technologies, including the part that boosts your CPU to really high frequencies in light single-threaded workloads. To better understand the performance tuning opportunities of the Ryzen 9 9950 X3D, let's have a look at its clocking and voltage topology. The standard Granite Ridge platform has a 48 MHz crystal input to the integrated CG PLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SLC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. As a whole, this provides CPU clock frequency granularity of 25 MHz. As with Zen 4 Raphael, each CCX has its own PLL, with the cores within that CCX running at the same frequency. In a typical operation, all cores within a CCX will run at the same frequency. The effective clock may differ if the core is in a different P state. When we switch to OC mode, we disable all automatic precision boost frequency boosting technologies and rely solely on the manual frequency and voltage configuration. The Ryzen 9000 voltage topology relies on a combination of internal and external power supply to generate the processor voltages. There are 4 primary power supplies from the motherboard VRM to the processor. The VDDCR voltage rail provides the external power for 3 internal voltage regulators. VDDCR CPU provides the voltage for the CPU cores in the CCX. On CPUs with multiple CCXs, like this Ryzen 9 9950X3D, each CCX has its own VDDCR CPU voltage rail, but the voltage is identical. The voltage rails can work in either regular or bypass mode, but on Granite Ridge, it's always in bypass mode. That means the voltage is always equal to the VDDCR external voltage. The VDDCR voltage rail is directly controlled by the CPU SMU using an SVI3 interface. On this motherboard, we can configure this voltage regulator in the BIOS. A crucial parameter is the VRM load line setting. The VRM load line is essential for 2 reasons, the VDROOP and the undershoot. The VDROOP is the decrease in voltage when the CPU goes from idle to load. You want your CPU to be stable in all scenarios, so knowing the lowest voltage the CPU runs at is very important. After all, if the voltage is too low, the overclock won't be stable. Undershoot and its counterpart overshoot is a brief voltage spike that occurs when the CPU switches from idle to load or from load to idle. While undershoot and overshoot are temporary spikes, an undershoot that's too low can cause instability. The VRM load line configuration is relevant to this overclocking strategy because we're switching to OC mode and disabling Precision Boost technology. That means that the CPU is no longer regulating the load line by itself, and we have to do it manually. Choosing the right operating voltage for our manual overclock is always a trade-off between increasing the overclocking headroom, managing the new thermal challenges, and of course, considering the CPU lifespan. With that last thought, we kick off our manual overclocking process. The maximum voltage will be determined by the application that we're tuning for. So the first step in our overclocking process is to determine what is the stress test that represents our worst case scenario. And for my stress test, I choose the OCCT CPU AVX2 stress test. The next step is to set a fixed CPU ratio and check the maximum temperature when running our workload. In my case, I pick a CCX ratio of 48x for both CCDs and a VID of 1.1 volt and level 6 voltage load line. This gives me a temperature of 70 degrees Celsius and an effective voltage of 1 volt. That means we can further increase the voltage until we get to about 90 degrees Celsius. Once we know the maximum voltage, we can tune the CCX ratio. Simply increase the CPU ratio until the application shows instability, then back off. This approach will give you the maximum stable per CCX frequency for a given voltage. In our case, we end up with a CPU ratio of 52x for CCD0, 52.50x for CCD1, and a core VID of 1.235 volt, which under high load drops to about 1.13 volt. If we try to compare the VF configuration of this OC strategy with the VF curve from OC strategy number 4, we can see that we've configured a single VF point on the VF spectrum as opposed to defining a curve that spans a range of voltage frequency points. Upon entering the BIOS, The boost frequency at one active thread is about 5250 MHz, and the average boost frequency gradually trails off to 5226 MHz when all cores are active. In light, single-threaded workloads, all cores in CCD0 can boost to over 5.2 GHz, and all cores in CCD1 boost to about 5.25 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. We see a pretty decent uplift compared to stock performance in most benchmarks. However, as expected, we also see some performance regression since the maximum frequency is now 5250 MHz, which is 500 MHz lower than the maximum 1T boost frequency with Precision Boost enabled. We got a maximum improvement of plus 43.83% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 5200 MHz and CCD1 effective clock is 5250 MHz with 1.127 volts. The average CPU temperature is 91 degrees Celsius. The average CPU package power is 292.1 watts. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 5200 MHz and CCD1 effective clock is 5250 MHz with 1.138 volts. The average CPU temperature is 79.7 degrees Celsius. The average CPU package power is 264.5 watts. Alright, let's wrap this up. The AMD Ryzen 9 9950X3D processor is definitely the flagship model of the Ryzen 9000 processor lineup. It features two CCDs, one with 3D V-Cache and another one that's pretty much the highest bin CCD that you'll find in the Ryzen 9000 lineup. The 3D V-Cache CCD actually has a lot of overclocking headroom, but unfortunately it's difficult to extract its full potential because we're dealing with two CCDs, and we only have one Fmax boost override option. So unfortunately, we can't quite squeeze everything out of that CCD. The non-Vcache CCD is the best one that I've seen across all of the Ryzen 9000 samples that I've tested. It can run 5.6 GHz with only 1.3 volt when all the cores in that CCD are active. Unfortunately, it doesn't have that much headroom, so I wasn't able to even squeeze it all the way to 5.95 GHz, which would be the Fmax boost override of plus 200. Anyway, that's it for this video. I hope you enjoy it. If you have any questions or comments, feel free to drop them in the comment section below. I'll also put up a written version of this video up on my blog as I usually do. And that's it. Thanks for watching and see you next time.